Welcome to the Deep Dive. This is the place where we take these huge stacks of technical reports, industry forecasts, and, the real cutting-edge research, and we boil it all down.
We turn it into the most informed, engaging conversation you're going to have all week. We're here to give you that shortcut to being truly well-informed.
Our mission today is a pretty deep exploration of where AI is meeting the physical world, the real economy.
Yeah, we're distilling the absolute forefront of enterprise AI adoption. We're going to be focusing on breakthroughs like digital twins and this fascinating new field of physics-informed neural networks, PNs.
And the massive challenges that come with that. I mean, deploying these systems responsibly across huge sectors like engineering, infrastructure, and even life sciences.
It's a huge task. We've pulled together an incredible set of sources for this, and they really illustrate this kind of duality.
Duality? How so?
On one side, you have this rapid, almost dizzying technical success, and on the other, you have the much slower but absolutely necessary human response.
The regulations, the impact on jobs, the ethical questions, all the headwinds.
Exactly. So this deep dive is really designed to give you the most important nuggets of insight so you can connect those dots yourself.
In a classic narrative, really. Speed versus control.
It is. We're going to unpack why companies are desperately trying to tap into hundreds of petabytes of data they've never used before.
And how AI models are now, unbelievably, being governed by the laws of physics.
Yeah, and why, despite all this incredible technology, only a tiny fraction of corporate AI projects are actually turning a profit.
Okay, let's jump right in. We can start with the enterprise adoption wave that's hitting boardrooms everywhere.
Yeah.
What we're calling the AI tsunami.
Good name for it.
So when AI first, really hit the public consciousness, we saw a lot of these generic applications, models trained on the whole internet, useful for, summarizing basic topics.
Right.
But our sources are all predicting that the future of enterprise AI isn't one massive chatbot on everyone's desktop. It's something else entirely.
It's deep, intricate customization. That's absolutely the shift we're seeing. Manu Verdas from NVIDIA, he points out that companies are moving way past the idea of having just one or two generative AI apps.
So what's the prediction then?
The prediction is that major companies will deploy hundreds of customized generative AI applications, all tailored to these tiny, minute parts of their business.
Okay, so give me an example.
I mean, anything from optimizing a supply chain just in Southeast Asia to helping a legal team draft a very specific type of regulatory filing. It's a total departure from that one-size-fits-all idea.
But that's the key question, right? How do you take a general model trained on, say, Wikipedia, and make it expert enough to handle a company's own proprietary, super specific, and often highly sensitive data?
That's where the magic is. That customization is completely dependent on linking those powerful large language models, LLMs, to the company's internal data.
And that link is something called RG.
Retrieval Augmented Generation, RAG. It's the essential bridge. Think of it this way. The LLM provides the intelligence, the fluency with language. But RAG connects it to the company's specific knowledge base.
Their documents, emails, their own research.
Exactly, everything. It produces accurate, contextually informed responses.
So if I'm a pharmaceutical company, I don't want the AI answering a question based on some general website.
Yeah.
I need it to answer based on my 20 years of clinical trial data that no one else in the world has.
Precisely. RAG ensures the model's output is grounded in verifiable company sources. It cuts down on the risk of, hallucinations while massively increasing relevance, and this is critical security.
And this is already happening at scale.
Oh, absolutely. This isn't a pilot project anymore. Our sources note players like Amdocs, Dropbox, Genstech, SAP, ServiceNow, Snowflake, they're all actively building new services using RAG and LLMs on their own high-value data sets. It's a core enterprise strategy now.
So what's driving this high-speed adoption, though? It can't just be the desire for customization.
It's also a cold, hard realization about infrastructure. Enterprises learned a very tough lesson in 2023.
Which was?
That trying to build and train your own foundational LLMs from scratch was not just difficult, it was prohibitively expensive.
An infrastructure sinkhole.
A total sinkhole. You're talking about massive specialized investment, tens of millions, sometimes hundreds of millions, in hardware, specialized software. It disrupts every other important company project. The cost and the talent required were just too high for most firms.
And that's the gap the cloud providers saw.
That's where they stepped in. They've become this necessary simplification layer. They offer the full-stack AI supercomputing and software needed to handle all this data.
They're basically removing the infrastructure headache for the company using the service.
That's it. This shift is fascinating because it's a trade-off. Companies are trading that huge upfront investment for a deep reliance on the cloud provider's subscription models.
But for the developers inside the company, it's a clear win.
Oh, an undeniable benefit. They can just embed API endpoints directly into their apps without worrying about the underlying compute layer at all.
Which frees them up to focus on the actual problem they're trying to solve,
Yeah,
the business logic.
exactly. It results in far more intuitive, responsive applications for the end users. And it just accelerates the pace of innovation inside the company because you've decoupled app development from infrastructure maintenance.
This shift toward deep customization really forces us to look at the fuel source for this whole revolution, which is, of course, the data.
Right.
Large corporations are sitting on these vast, untamed digital oceans. We're talking high hundreds of petabytes for a major enterprise.
It's a staggering amount of information.
And yet many of them report that they're mining less than half of that for any kind of actionable insight. It's just an insane waste of potential knowledge locked away.
It is, and that's precisely where generative AI provides the key. For decades, traditional data analytics has really struggled with unstructured data.
Anything that doesn't fit neatly into a spreadsheet.
Right, rows and columns in a database. But now, businesses are finally starting to use generative AI to mine that raw, untamed data. Internal chats, proprietary videos, code repositories, complex PDFs.
So Gen AI isn't just about generating new content. It sounds like its real near-term value might be in finally making sense of the content companies already have.
Exactly. And that capability is essential for two big reasons. First, it gives you the clean, high-context data you need to customize your LLMs with RAG.
And second,
Second, and this is crucial, it's the feedstock for training multimodal models. This is where we move beyond just text-only AI.
okay, this is where it gets really interesting. Multimodal LLMs. They're poised to combine text, speech, images all together.
To deliver these incredibly relevant responses, imagine a manufacturing tech, right? Standing in front of a complex machine.
Yeah.
They could take a picture of a schematic, speak their technical question, and the AI could synthesize the text from the maintenance manual with the visual information from that picture to give them a precise, actionable answer right there.
The practical impact of that is just enormous. It must cross multiple sectors.
Oh, absolutely. You look at healthcare, multimodal AI can help with anomaly detection on health scans. It's incorporating the visual data from the image with the patient's written history and the doctor's notes.
And in retail.
It helps uncover emerging trends that are hidden in video data of customer behavior combined with their chat logs. And across all industrial settings, it just makes operations measurably safer.
By synthesizing all these different sources at once.
Exactly, like correlating a sudden temperature spike in a video feed with an anomaly in the vibration logs from a sensor.
This ability to process and understand these vast, diverse data sets at speed is why AI is now being seen globally as a national treasure.
It is. It's kicked off a new kind of space race. Every major country is aiming to create these centers of excellence to drive advances in research, science, and ultimately, improve their GDP.
What's so fascinating is that the barrier to entry, financially, isn't what it used to be.
Not for a sovereign nation, no. The costs are large, but not astronomical. Countries can build these highly efficient, exascale AI supercomputers with just a few hundred nodes of accelerated computing.
And these government-funded centers are meant to do what exactly? Boost the economy.
Boost economic growth, secure talent, and build stronger university programs to train the next generation of scientists and engineers. It's a foundational move for global competitiveness.
Because the power to compute, the power to innovate, is rapidly becoming the most valuable resource a nation can have.
It really is.
So the ability to build AI is becoming a core national security and economic issue. It's accelerating this whole transition to the next phase of computing infrastructure globally.
That's a perfect way to put it.
Okay, so if that first section was about the brain of AI, the large models, the data that fuels them, then section 2 is really about its body, how AI interacts with the physical world through digital twins.
Right. We're pivoting from corporate data centers to the vast, complex systems of engineering and infrastructure.
So let's start with the basics. The digital twin, or DT, framework.
What is it? It's the connective tissue between the digital and the physical. A DT is a precise digital representation of a physical system. It could be a jet engine, a manufacturing line, a building.
Or even an entire city.
Or an entire city. But the real change is the integration of AI. That's what's transforming these static representations into intelligent, autonomous entities that can think, predict, and ultimately act on the physical world.
To really get a handle on the leap we're making here, our sources talk about a four-stage life cycle of a modern digital twin. It's a progression.
Yeah, it's a continuum that starts with the basic model and goes all the way to full autonomy. Let's walk through it.
Okay.
Stage one is modeling. This is just creating the twin itself. You often use a combination of traditional physics-based models and, crucially, physics-informed AI, which we'll get into in a minute.
And stage two.
Stage two is mirroring. This is the essential real-time sync. The digital twin is constantly updated with live data streaming from the physical asset sensors, logs, operational inputs. It's a living model.
That real-time data link, the mirroring, that's what makes it so much more useful than just a simulation, because it reflects reality right now, including all the wear and tear.
Exactly.
But isn't that incredibly expensive and complex to maintain,
Mm.
especially for thousands of legacy assets?
Yeah.
I mean, what happens when the twin data inevitably drifts from the physical asset?
That difficulty is precisely the challenge companies are solving right now. They realize perfect mirroring is often impossible, which is why the AI becomes necessary.
Ah, okay.
The AI detects that drift, it learns the relationship between the twin and reality, and it uses that learned knowledge to enter stage three, intervention.
So the twin starts acting on the real world.
It acts through highly specific prediction, anomaly detection, optimization strategies. It tells you what to do and when to do it.
And stage four is where it gets truly futuristic.
Yes, stage four is autonomous management. This is the leap where the DT evolves into a cognitive system. It's not just reporting problems anymore, it's capable of reasoning, creative scenario generation, complex decision-making.
And this is where the large language models come in.
Often, yes. Leveraging LLMs and foundation models to manage the physical system with minimal human input, effectively running a complex plant or an electrical grid on its own.
The aerospace sector, just because of the high costs and safety needs, has been a pioneer here. Our sources highlight some pretty established use cases.
They really have. Rolls-Royce, for example, uses digital twins not just for monitoring, but to customize repair processes for specific engine parts.
So it's not a generic repair plan.
Not at all. Since every engine experiences unique stresses, the twin lets them optimize maintenance based on the specific history of that one component. It saves a huge amount of time and material waste.
And on the safety side, Boeing famously used DTs for the 787 Dreamliner's battery systems.
Yeah, a critical system. They use the twins to improve safety, manage thermal risks, and proactively monitor the system's health in flight.
Airbus too, right, with the A350?
Exactly. Airbus uses them for real-time performance monitoring. And this is translated directly into substantial, measurable improvements in fuel efficiency and lower emissions, just by constantly optimizing the aircraft's operational profile based on real-time conditions.
So, okay, let's dive into the technical core of that modeling stage, this absolute breakthrough that's enabling this next generation of digital twins. Physics-informed neural networks, or PNNs.
Yes.
It almost sounds like we're forcing AI to go to engineering school. What is the core concept here? Why is it so revolutionary?
It's revolutionary because it solves a fundamental problem with traditional AI models. They're often statistical black boxes. You don't know why they're making a decision. The core concept of a PNN is really elegant. It incorporates the governing equations of physics, things like conservation laws, or the equations that describe fluid flow, structural mechanics, heat transfer. It bakes them directly into the neural network's loss function.
Okay, so wait. Instead of the AI only being penalized if its output doesn't match the observed data from a sensor,
Right.
it is also penalized if its output violates the known immutable laws of the universe, like, say, conservation of energy.
Precisely. It's like having a strict physics professor standing over the shoulder of the AI model. This allows the AI to combine data-driven learning, what it observes, with physics-based causality, what must happen based on first principles.
And the benefit of that is speed.
Immense benefit in what we call accelerated engineering. These physics-informed AI surrogate models enable simulations that are just orders of magnitude faster.
Give us the scale here. How much faster are we talking about?
Sources indicate these models can be up to 1,000 times faster than traditional numerical solvers, like finite element analysis.
So something that took weeks can now take
Seconds or minutes. It allows for real-time product performance feedback to be incorporated instantly during the design phase. The speed is critical for iterating new designs rapidly.
That speed is transformative. But what I found truly surprising is the capability of PNNs in solving inverse problems.
Explain why those are such a headache for engineers.
Yeah, inverse problems are notoriously difficult because they defy the normal flow of logic. A forward problem is easy. I give you the parameters, material, force, temperature, and you predict the outcome.
Okay.
An inverse problem is the reverse. You observe the outcome, a vibration, a tiny crack, and you have to try to determine the unknown parameters that caused it, the internal forces, the material properties.
It's like friends up engineering. You're trying to look backward through a chaotic system.
That's a great way to put it. And it's incredibly challenging, especially when your data is sparse or noisy.
So give us a real-world example where PNNs are actually doing this.
The case study on pre-stressed concrete beams is perfect. These are the massive, critical structures you find in bridges and large buildings.
Right. Two key parameters, the pre-stress force on the steel tendons inside and the concrete's elastic modulus, are extremely difficult to measure directly, especially years after it's been built. You can't just cut open the concrete to measure the tension.
So how does the model figure out what it can't possibly see?
Using these advanced PAN models, specifically something called MFR-PINNs, engineers can accurately identify these invisible structural parameters using only sparse and noisy experimental observations from the surface, like deflection measurements.
Because the physics are baked in.
The physics equations governing the structure are embedded in the AI, forcing it to find internal parameters that are physically consistent with what's being observed externally.
And the results here are genuinely revolutionary for infrastructure maintenance. I mean, the sources highlight incredible precision.
They're amazing. The model showed minimum relative errors for the elastic modulus as low as -6.49%. And for the pre-stress force, a remarkable minimum relative error of just 0.65%.
Those numbers are unbelievable given what they're predicting.
Yeah. This capability is critical for long-term service assessments of our civil infrastructure. By integrating physics with just a few sparse measurements, these models can predict the continuous state of the structure and identify these key parameters. It's turning sparse data into deep, actionable, physics-backed knowledge.
Beyond just simulation in these inverse problems, AI is fundamentally shifting the role of the design engineer. We're moving from iteration build, test, fail, repeat, to just pure innovation-led design.
Absolutely. We see AI helping engineers optimize material layouts for maximum strength with minimal weight, a process called topology optimization.
It's generative design, but informed by physics.
It is. The AI can explore a design space that's vastly larger than any human team could, finding these unique structural solutions that are lighter, stronger, more efficient, all while strictly accounting for real-world physical constraints: fatigue, thermal limits, manufacturing. The AI is truly co-creating with the engineer.
And this capability isn't just hidden behind the scenes. It's translating directly into the consumer experience. It's making that whole research and purchasing cycle way more interactive.
Exactly. Generative AI is powering these sophisticated, realistic customer experiences. Think of advanced car configurators with hyper-realistic 3D visuals, or augmented reality demos that show how a new fridge will fit in your kitchen.
Virtual test drives.
Virtual test drives that incorporate physics to give you a real feel for handling and acceleration. The barrier between digital simulation and the consumer is just dissolving.
And crucially, this technology is addressing arguably the most sensitive engineering challenge today: autonomous vehicle safety.
A huge one. Generative AI is enabling significant breakthroughs in AV development.
What's a core problem it's solving?
The problem with testing AVs in the real world is that dangerous or rare scenarios happen, well, rarely, and you can't ethically run millions of dangerous tests on public roads.
So Gen AI solves this how?
It takes recorded sensor data, real-world inputs, and transforms it into these fully interactive, massive 3D simulations. They are, in effect, digital twin environments of the road, the traffic, the weather.
So you turn a recorded drive into a fully editable virtual world.
Precisely. And these environments, combined with generating synthetic data, are essential for safety validation. Developers can safely test and validate AVs virtually at scale. You can simulate millions of miles of corner cases, bad weather, dangerous human drivers, all safely before that vehicle ever hits a real road.
Okay, so moving from design innovation to operational resilience, let's explore how AI is keeping the physical world actually running. The core idea here is predictive maintenance.
Right, using real-time IoT sensor data, machine learning, analytics, all to speculate on machinery failure and achieve proactive repairs. The goal is to drastically minimize unexpected downtime.
And the predictive maintenance flow, it's pretty intensive. It's not just running a simple algorithm.
Not at all. It starts with collecting high-frequency data on things like temperature, vibration, pressure, electrical current. But the heavy lifting comes right after that. Rigorous data processing and cleaning.
Why is that cleaning step so critical?
Because raw sensor data is a mess. It's often fragmented, noisy, inconsistent. You have interference, calibration drift, transmission errors. If you feed bad data into a deep learning model, you get useless results back.
Garbage in, garbage out.
The classic problem. So cleaning, normalization, synchronization, feature engineering, all non-negotiable steps before you can feed that high-quality input into the AI models. The success of predictive maintenance really hinges on the quality of the data prep.
Okay, let's look at a specific industrial challenge that plagues manufacturing floors everywhere. Belt failures in motor-driven systems. They're common, frequent, they cause massive downtime. How does AI tackle something that seems as simple as a degrading industrial belt?
This is a perfect example of combining specialized monitoring techniques with robust deep learning. The approach involves using something called motor current signature analysis, or MCSA.
What's that?
It looks for subtle anomalies in the electrical signature of the motor that actually reflect mechanical stress. And you combine that with specialized deep learning models that are good at recognizing time-based patterns.
And those specialized models are LSTMs, long short-term memory networks. Why is an LSTM better for this kind of gradual degradation monitoring compared to other types of neural nets?
LSTMs are a specialized type of recurrent neural network designed precisely for sequential data, like the sensor readings we're talking about. They excel at modeling sequences that have long-range dependencies.
And traditional networks can't do that.
They struggle with something called the vanishing gradient problem when they try to learn patterns over long time periods.
Explain the vanishing gradient problem in simple terms.
Okay, imagine a simple AI trying to remember a key vibration event that happened 100 days ago while it's constantly processing new data every second. By the time it processes yesterday's data, the signal from 100 days ago has basically faded out. It's vanished.
I see.
LSTMs overcome this using internal memory cells and gating mechanisms like digital locks and filters that regulate the flow of information. They specifically decide what information to keep, what to forget, and what to update.
So they're excellent at learning that slow decline in health, not just a sudden failure.
Exactly. And once the model is successful, the output becomes incredibly actionable. Successful models accurately forecast these degradation trends. Those results are then mapped onto a simple 3-tier risk scale: green, yellow, red.
Fault-oriented prescription.
That's the term. It lets maintenance teams shift entirely from expensive, scheduled maintenance to prioritizing interventions based on actual risk and predicted remaining useful life.
Which brings us back to the challenge of scale. It's one thing to monitor a single machine. It's another thing to manage a whole fleet of thousands of them, especially when new assets have no historical data to train a model on.
That issue of generalization across a fleet is the next frontier. A case study on hydraulic test beds showed how critical scalable data transformation models are.
How so?
When degradation data was sparse or just unavailable for some assets, using a scalable data transformation model improved predictive performance significantly.
Give us the numbers on that improvement.
For those specific assets where data was limited, the scalable model achieved 71.74% performance. Without scaling the data model, it was only 64.13%.
That's a big jump.
It is. It demonstrates that for these digital twin intelligence models to be deployed across an entire enterprise, careful data standardization, transformation, and scaling are non-negotiable for getting reliable insight.
Now, when we talk about safety-critical diagnostics, aviation is the absolute pinnacle. Engine reliability is everything.
It's the cornerstone of safety and efficiency. And AI has moved way beyond simple failure prediction here. The focus now is intensely on remaining useful life RUL estimation and sophisticated real-time anomaly detection.
And the models they're using are at the forefront.
Oh, yeah. We're talking about advanced architectures like 1D CNNs, one-dimensional convolutional neural networks. They're highly efficient at pulling features directly from raw time series inputs.
And they also use something called bil-LSTMs, or bidirectional LSTMs. What does going bidirectional add to the prediction?
So a standard LSTM processes data chronologically, past to present. A bil-STM processes the data in both directions, forward and backward.
From the future to the past.
Exactly. It gives the network enhanced context awareness. For RUL estimation, it means the model can correlate a current data point not just with what happened yesterday, but also with what happens immediately after an anomaly is detected. It gives it a more robust, holistic understanding of the context.
But the major hurdle in aviation isn't just accuracy, it's the need for absolute interpretability. When a decision is safety critical, like grounding an aircraft, you can't rely on a black box model.
Absolutely not. You have to know why it made the decision.
So how do they balance that demand for accuracy with the mandate for transparency?
They rely heavily on hybrid approaches. They combine physics-based digital twins, which simulate engine behavior using known thermodynamic principles, with these AI-driven learning models.
So the physics provides the baseline.
The physics model provides the baseline understanding and structure, and the AI refines it based on the operational data. This meets the standards for both accuracy and interpretability. You get transparent, justifiable outputs that regulators and engineers demand.
But adoption still faces some pretty big operational constraints.
It does. It's largely centered on data quality and computational demand.
What's the data challenge?
It's enormous. Sensor data is often fragmented across legacy systems, it's noisy, and crucially, it has sparse labeling, especially for rare, catastrophic failures. I mean, if a type of failure has only happened twice in the entire history of the fleet, the AI model has very little to learn from.
And then there's the computational bottleneck in the air.
Exactly. These deep learning models require substantial memory and processing power. This can easily exceed the capabilities of the embedded avionics systems, which have really stringent energy and thermal constraints.
So you need lightweight models.
You need highly optimized, lightweight models that can operate reliably within the limited processing power of the aircraft systems. It's a major engineering challenge in itself.
Okay, let's pivot now to civil infrastructure, specifically bridges. When we look at bridge failures, it's a complex mix of factors.
It is. You have internal factors like design errors or poor maintenance, but externally, 65 to 70% of failures are attributed to natural causes. Floods, earthquakes, avalanches. It's a mix of nature and negligence.
And when you look specifically at the U.S., our sources cite poor infrastructure knowledge and just a persistent lack of annual maintenance as prominent reasons for major failures.
We have thousands of aging structures. This just reinforces the need to move beyond scheduled visual inspections and into continuous AI-powered monitoring.
Which brings us to AI-enhanced structural health monitoring, or SHM. How does AI radically improve on the old method of just checking a bridge once a year?
Well, SHM systems now use multimodal sensor inputs. We're talking about a comprehensive network of strain gauges, accelerometers, advanced MEMS sensors.
To get a holistic view in real time.
A holistic understanding of structural integrity. And these AI-enhanced systems have been shown to detect structural anomalies, like the initial formation of microcracks, up to 25% faster than conventional methods.
That speed is absolutely crucial for averting catastrophic failures. And what role does computer vision play in inspecting parts of a structure that are really hard to access, like the underside of a massive bridge?
Computer vision, using AI, is vital for that remote damage detection. Engineers are deploying drone-mounted cameras and feeding that visual data into high-speed object detection models.
Models like YOLO 5.
Exactly. It's a highly efficient, one-stage object detection model.
What makes it so effective for this?
It's speed. It processes data at 38.4 frames per second, which is 63% faster than its predecessor. That incredible speed makes real-time crack detection on vast concrete bridges highly efficient and practical.
So it's not about analyzing a static image later, it's instant identification as the drone flies.
That's it. And to handle that massive influx of data from all these sources, strain gauges, accelerometers, video feeds, and still maintain rapid response times, they're pushing the processing power out of the central data center.
Out to the edge of the network.
Right out to the edge. Wireless sensor nodes are increasingly equipped with edge computing capabilities. They process the massive stream of data locally right at the bridge structure itself,
Which cuts down latency.
dramatically reduces latency, and enhances the system's ability for real-time decision-making, which is non-negotiable for monitoring structural integrity.
We spent a lot of time detailing these monumental technical breakthroughs, but now we really have to look at the human systems these technologies impact, starting with life sciences and the very delicate world of medical regulation.
Great. AI is radically transforming pharmaceutical R&D. It's fundamentally accelerating the drug discovery and validation cycle from years down to months.
The molecular breakthroughs are just staggering. Models like DeepMind's AlphaFold and Meta's ESMFold have essentially revolutionized protein structure prediction.
What used to take years of complex, expensive crystallography work, figuring out how a protein folds, now takes mere seconds of computation.
which frees up researchers to focus on design.
Exactly. And innovation is pushing even further into generative chemistry. We're seeing new open source models like BoltzGen emerge. They generate novel, functional protein binders with physics and chemistry constraints built right in.
So they're generating potential new drugs.
Yeah. Potential therapeutic compounds that address difficult to treat diseases. These AI tools are helping manipulate biology to solve disease in ways we haven't even imagined yet.
But all this optimism is heavily tempered by significant risk in the AI medical device space. Our sources are warning that the high promise of these devices isn't yet supported by robust clinical evidence.
The speed of innovation has just outpaced clinical validation. Only a tiny fraction of cleared AI medical devices are backed by randomized controlled trials or any kind of comprehensive patient outcome data.
And this lack of robust validated evidence has real-world consequences.
It does, and regulators are now grappling with it. We have reports of patient harm, device malfunctions leading to injuries, and in one reported case, a death attributed to an AI-informed device.
And then there's the bias.
Severe algorithmic bias risk. For example, the ICU triage tool that was found to under-identify Black patients for necessary life-saving extra care, all because of biases in its training data.
And there's also the subtle problem of automation bias.
A huge problem, where clinicians' own detection rates fall because they become over-reliant on the AI assistant's recommendation, and they start to overlook obvious signs of risk themselves.
This regulatory vacuum is why the FDA is stepping in so strongly now. Their 2024 finalized guidance and the January 2025 draft guidance, they establish incredibly high compliance expectations.
The mandate is absolute, and it elevates AI from being some IT experiment to a strictly regulated medical product. If AI informs anything critical labeling, performance claims, dosing, safety, clinical decisions, then the entire solution has to meet device-level quality, validation, and lifecycle controls.
So for the IT and AI development teams, this means they now have to operate under these stringent good practice or GXP standards.
Yes, it requires design control rigor, traceability, knowing exactly which data point trained which part of the model provenance, explainability, comprehensive model lifecycle management, drift monitoring, bias detection. The FDA is signaling that AI risk is now a business risk and governance is non-negotiable.
Okay, shifting focus now to the labor market. The discussion around AI and jobs is still heavily contested, especially in the software development world.
It is. Many developers see AI tools as this massive augmentation, raising the bar on what engineers can do and dramatically increasing productivity by handling all the rote stuff.
But augmentation often leads to inevitable restructuring. We have accounts from startup environments where leaders are reporting a shift. They're replacing junior developers, the grads, with powerful AI tools like Claude,
which can handle basic code generation and debugging.
And if the lead engineer can handle the high-level problems and just rely on AI for the basic implementation, well, that can lead to replacing mid-level and sometimes even senior developers.
It creates a leaner structure, fewer people, faster communication, quicker turnaround. But as someone who started in those junior roles, I find that frightening. The rote stuff is how you learn the fundamentals. If AI handles all the implementation, how do the grads ever build the foundational intuition they need to recognize why a design pattern works or why code is buggy? That knowledge might just disappear, creating a huge skills gap down the line.
Yet a lot of senior developers feel safe. They argue that AI cannot yet correctly interpret complex, non-trivial requirements, especially when the clients themselves aren't even sure what they want.
Right. They argue that they've spent their whole careers cleaning up buggy code produced by cheaper, faster outsourcing. And this new generation of AI-generated code will be no different. Fast, but often lacking context and architectural integrity.
They believe that critical thinking, systems architecture, translating ambiguous human requests into precise technical requirements that will remain a purely human domain.
For the foreseeable future, yeah. That's where the true value add is.
If we look at the risk classification based on the nature of the work itself, the pressure points become really clear.
Yeah, work that is clerical, repetitive, precise, and perceptual data entry, basic image processing, routine code generation, is highly susceptible to automation.
Conversely, occupations that require high-level coordination, deep creativity, and intense, nuanced human interaction are proving to be far more robust.
Education, the arts, high-level legal strategy, complex management, certain social services where emotional intelligence is just non-negotiable. The value is shifting from efficiency to humanity.
Finally, we have to put all this immense hype and enthusiasm into a financial perspective. While the promise of productivity gains is huge, an MIT study uncovered a pretty sobering reality.
Yeah, that 95% of corporate AI initiatives failed to turn a profit.
95%. That statistic is stunning, especially considering the massive investment.
It is. It suggests the problem isn't technical failure. The models usually work as intended. The failure is driven less by the algorithm and more by poor execution and strategy, by chasing fads without doing your due diligence first.
So what does that due diligence failure look like?
It's multifaceted. It includes a poor internal data strategy, companies rushing to deploy AI before their own data is cleaned, standardized, or accessible via array.
It also involves over-relying on vendor claims without proper internal validation.
And most critically, it's a lack of executive buy-in for the necessary cultural change. AI adoption is a business process transformation, not just an IT upgrade. If leadership isn't willing to restructure teams and workflow to leverage the AI, the initiative will fail, regardless of how well the model performs.
This brings us to the ethical and legal foundation supporting these incredibly powerful and increasingly autonomous systems.
Right.
Knowledge is powerful, but when that knowledge is codified into AI, it inevitably reflects and amplifies the biases that were present in its training data.
And we've seen some really troubling examples that show how systemic biases in historical data become automated and magnified. A notable case is the Compass sentencing software.
Right, used in some U.S. jurisdictions.
It was found to be strongly biased against Black Americans, more likely to incorrectly predict they would reoffend compared to white counterparts with similar criminal records. The system learned historical disparity and just codified it as statistical probability.
And this bias isn't always from explicit inputs like race or gender. Recruitment tools, like one used at Amazon, showed a severe gender bias.
Yeah, the system learned to prioritize male characteristics and downgrade applications from universities with a strong female presence, even without any explicit inputs about gender. The AI just inferred these sensitive characteristics from seemingly neutral information.
This leads directly to the core problem of transparency and accountability, the infamous black box problem.
Right. As algorithms get more complex, like these deep learning models we've been talking about, their decision-making process often becomes opaque. It makes accountability incredibly difficult when harm occurs.
This opacity has major implications for the legal system, especially when an autonomous agent, an AA, is involved in an accident or a financial loss. Criminal liability requires mens rea, the intention to commit a criminal act.
And if an autonomous agent acts unpredictably, say, an AV makes an unexpected maneuver, or a trading bot executes a million bad orders, it becomes incredibly challenging to prove the intention of the human programmer.
The agent may perform the criminal act, the actus reus, but the voluntary aspect of the human action is contentious.
Exactly. This complexity could create an incentive for human agents to avoid knowing precisely what the machine is doing, just to deny liability. It muddies the waters of responsibility.
And the financial markets, where autonomous agents dominate trading volume, have already seen these risks at scale.
Oh, yeah. The Knight Capital Group incident in 2012 resulted in a $460 million loss because an automated trading agent just erroneously submitted millions of orders within minutes.
And research has shown that these AAs can even learn malicious market manipulation techniques on their own.
Yeah, through reinforcement learning. They can learn things like order book spoofing just by optimizing for profit within the rules they're given. It illustrates the inherent financial risk when these complex autonomous systems operate at high speed.
The ultimate ethical battlefield right now, though, it really seems to be autonomous vehicles. They raise such profound ethical dilemmas.
They do. Consider the classic no-win crash scenario where the car has to make an instantaneous decision. Prioritize the safety of the passenger inside or prioritize the safety of pedestrians outside.
And the difficulty lies in the fact that there's no standard ethical approach programmed into these systems.
None. Should the system follow utilitarian ethics, seeking the greatest good for the greatest number? Or should it follow deontological ethics, focused on strict rules like always protecting the life of its owner? The complexity is that many of these philosophical approaches just can't solve such highly nuanced real-time problems.
So the AV is forced to make an immediate judgment call under uncertainty, with potentially fatal consequences. And who's responsible when that call goes wrong?
That's the question. The lack of standards for accident investigation, combined with the proprietary nature of the data logging systems in AVs, severely complicates accountability. Authorities often have to rely on the cooperation of the manufacturers just to get the data they need.
Which is an inadequate standard for public safety. Who should choose the ethics that govern that split-second decision? The driver, the manufacturer, the regulator.
The problem of programming morality into a machine that operates outside of immediate human control remains one of the most pressing questions of our time.
So this deep dive, it's really revealed two powerful and often contradictory parallel stories that are unfolding right now.
They are. On one hand, you have these monumental, sometimes dizzying technical breakthroughs in engineering and the physical sciences.
We've tracked digital twins moving into full autonomy, the emergence of PINs accelerating complex simulation by thousands of times.
Yeah, allowing us to solve inverse problems in concrete bridges that were previously impossible. We've seen specialized LSTMs give us these highly prescriptive, risk-based maintenance instructions. We've covered AI accelerating drug discovery from years down to months. The technical capability is just staggering.
But that parallel story is the slow, grinding, yet absolutely necessary process of the human system trying desperately to keep pace with that innovation.
We covered the FDA imposing GXP traceability, validation, and bias monitoring on AI medical devices in response to actual patient harm. We looked at the labor market pivoting to define where human creativity is irreplaceable.
And we dissected the complexities of proving mens rea when an autonomous agent causes hundreds of millions in financial losses.
It's a fascinating contrast. We have AI that can predict the remaining useful life of an aircraft engine or the structural stability of a bridge with incredibly high precision thanks to these physics-informed models that obey the laws of conservation.
And yet, as a society, we struggle profoundly to predict the legal liability, the unintended biases, or the broader social and economic impact of the AI systems themselves.
That's the big question.
So, given that this technical innovation is so clearly outpacing governance and regulation, is it enough to simply mandate transparency so we can only see what the AI did after a catastrophe occurs? Or must society collectively define the fundamental, non-negotiable ethical doctrines, the core values that protect public safety and fairness, and demand that engineers program those doctrines into every new autonomous system before it gets deployed into the physical world?
That is the critical question. Do we need a consensus on ethical boundaries for autonomy before we grant these systems complete control over our infrastructure, our health, and our financial markets?
Something profound to mull over until our next deep dive. Thanks for listening.